Alright, hi. Today we're going to be dealing with this particular problem, and we're interested in, I'm just going to kind of draw a picture here. You can read it while I'm drawing the picture, but here's my x and y axis. This is the gist of the problem. We have a semicircular rod like this, and we're interested, the rod has a charge on it of -q, and we're interested in the electric field that emanates from this charge at the origin. Okay, so for a problem like this, I'm going to hide this layer now. For a problem like this, what we want to do is pick out just a chunk of this charge. So there's the chunk of this charge here, and that little chunk I'm going to call little dq, like that. I could call it with a lowercase or an uppercase q, it doesn't really matter. And so I'm going to focus in on, here's my vector r like this. I'm going to just kind of define some variables. I'm going to call this angle here theta, so we can have some things to talk about. And let's say that the semicircular arc has radius capital R, like that. Okay, so all of that's pretty straightforward. We're interested in the E field here, so I'm going to use the equation that we've been using to determine the E field. So dE is 1 over 4 pi epsilon naught, sometimes people just call that K, times dq, and again I could write that as a lowercase q or an uppercase q, over r squared with the r unit vector, there like that. Okay, so this is looking pretty good. Now what I'd like to do is really dissect this equation, because everything is going to come from this equation. So the first piece I'm going to focus on is this dq here. Okay, so sometimes it's easiest when you're trying to figure out what dq is to look at this fraction, dq over q. Now this sort of necessitates a new picture here. So here again is my arc. Let's see if I can draw some straight lines. Okay, so there's my arc. And what I'm interested in is what the ratio is between this dq here and the entire q on the entire length of that arc. So really what I'm thinking about is kind of some d theta here, right? And so what I notice is that dq over q, the ratio of this chunk of charge to the entire charge, is the same as the ratio between that chunk of angle, d theta, and the entire angle of that arc. And the angle of this arc starts at 0 and goes to pi. So really, this is just pi here. You may want to pause the video, make sure that this makes sense to you here before you move on, because this is a pretty important piece of the puzzle. Okay, and it might make sense at this point to really note that in our problem we're going to start with dq kind of at the top here and sort of sweep all of the dq's all the way to the bottom. So that means that we're starting with an angle of 0. Again, look at where your theta is. So we're starting right at the top there when theta equals 0, and we're sweeping all the way down to when theta is pi radians. Okay, so that's kind of helpful. Sometimes it's nice to sort of write a little side note like that. Okay, now let's focus in on what this r hat and r squared business is all about. So first let's remember what r really is. So r is defined as r observation minus r source. So our observation is the point of observation. Here we're standing at the origin and trying to determine the E field emanated. So the origin is just 0, 0, 0, of course. And the source of our charge, or the source of our E field in this case, is way up here. Okay, so let's draw actually one more picture here. That's maybe just a little bit simpler. So you can imagine here's my dq like that, and here's my angle theta right here. So my r goes down here, points kind of down towards the origin like that. If I'm interested in my rx, that points this way, right here, rx, and my ry will point downward, right? So the r of my source, in this case, reminding ourselves that the radius of the arc is capital R, is going to be negative r sine of theta times positive r cosine of theta, 0, just like that. Okay, great. So far we're looking pretty good here, and so really we've got that this is just going to be, let's see, so we're just negating our negative sign, so we're just going to have r sine of theta negative r cosine of theta, 0. And this makes sense in this picture that we've drawn, right? We end up with a positive rx that points to the right, a negative ry that points down, and 0 in the x or in the z direction. Okay, now so that's our r vector, and then we have the magnitude of our r vector is always going to be capital R, right? No matter where we are on this arc, the distance between dq and the origin is always capital R, so that's great. And then we're going to look at our r hat, which is going to be the r vector divided by the magnitude of r. So in this case, I'm just literally going to take this and divide out the r. So I just end up with sine of theta, negative cosine of theta, and 0, like that. Okay, so this is pretty cool. So let's plug all of this into, again, this main equation with this dE. That's the thing that I'm really the most interested in. So dE, I still have the 1 over 4 pi epsilon naught. Nothing happens there. That's still hanging around. My dq I can now replace with d theta over pi times q. So one thing that I should have noted here is that our q is negative, so really that should be a negative q there. So if I wanted to, I could write this out in a separate line. dq is negative d theta over pi times q, like that. Okay, so now let's plug that in right here. So this is going to be times d theta times q, all divided by pi. So there's my dq. So I plugged that in. Now I have to divide by the magnitude of r squared, which is just 1 over capital R squared. And then we have an r hat here, which is sine of theta, negative cosine of theta, 0. Just like that. Okay, so far things are looking really, really good here. Okay, I'm going to draw one more final picture of this arc of charge here, if it'll let me. So what I have, here's the arc like this. And one thing that we'll notice is that, here's our dq hanging out up here. So this gives us a dE that maybe it points down like this. But there's a symmetric chunk of charge down here that'll give us kind of the same but opposite reaction right up here. So what do you notice about the y components of these two E fields? You should notice that they cancel out. So our dEy is going to be 0. So all the contributions from those dEy's sum to a 0. And what we'll notice is that we then kind of double the x component, right? So that's something that we do want to kind of focus in on now. Okay, so let's focus in on the x component, and I can show you in a moment mathematically how to get that y component. Okay, so E sub x, so we're just looking at the x component of dE. So that's just the integral of dE sub x. I can't put bounds on here yet because I don't know what I'm dealing with. So right now, all I'm going to do is focus on the x component, which is just going to be the sine of theta. Okay, so everything else is going to come out in front except for things involving thetas, because my d theta will be in my integrand here. So what do we have? We've got 1 over 4 pi squared epsilon naught capital R squared, like this. Then I'm going to, let's see, I have actually a q on top also, so that's really a q there, pardon that. And we have a negative sign there like that, and everything else is going to go inside of our integral, so we have sine of theta times d theta, like this. And we already figured out that our thetas start at 0 and go to pi. Again, you can think about why that is, given where the theta is defined. Okay, so now this is actually really straightforward, and it's really just kind of a plug and chug question, right? This is really just a calc question at this point. So let's keep chugging along here. So what do we end up with? We're going to have all this stuff on the outside. That's going to stay where that is. Epsilon naught r squared, like this. Okay, the integral of sine of theta is negative cosine of theta, and we're going to evaluate this from 0 to pi. At this point, it might make sense to remind yourself what cosine of theta versus theta looks like. So remember, cosine of theta looks something like this. Okay, obviously 0 is going to be out here, and pi is right here. Okay, So really what we have is we're going to have this whole business out in front here, 4 pi squared epsilon naught r squared, like this. So we have a negative cosine of pi minus a negative cosine of 0, like this. So this should be what we have here at this point. So let's see, cosine of pi, this little piece right here, that's -1. So I have a negative 1 plus cosine of 0, which is 1. So this whole thing gives me a positive 2. So this just becomes negative q over 2 pi squared epsilon naught r squared, like that. Okay, and so that would be our final answer for our e sub x. You can do the exact same thing with e sub y, where instead of sine of theta here, you have a negative cosine of theta. The reason for that is because of this, right? Instead of focusing on the x component, you would focus in on the y component. And if you do that, and if you evaluate at the same integral bounds, you will see that it actually cancels out. Okay, thanks so much for watching, and I look forward to seeing you next time.